So first, today we're going to be doing exercise 1.3 in NCERT class 9 of the chapter number systems. So let's get right to it. The first question in exercise 1.3 has 6 parts. It says, write the following in the decimal form and say what kind of decimal expansion each has. So the first part over here, 36 by 100. Now 36 by 100 can be written in the decimal form as 0.36, which means that this has a terminating decimal expansion. We'll move to the second part. Second part is 1 by 11. Now if we divide 1 by the number 11, and I'll just use this part of the sheet for my rough calculation. So this will be of the form 0.0909 and so on, which means the 09 will keep repeating itself. So we can say that this is a non-terminating expansion, but it is recurring. Third part is 4 and 1 by 8. If we convert this into a regular fraction from a mixed fraction, we get the number 33 by 8. And if we divide 33 by the number 8, this is what we get. And finally, we get 0 as the remainder. So 33 by 8 can be written in the form 4.125, which is a terminating decimal expansion. Fourth part is 3 by 13. Hence we get the number 0.230769, and this entire 6-digit sequence keeps repeating itself. So we can see that this one is a non-terminating sequence, but a recurring one. Now moving on to the fifth part. The fifth part is 2 by 11. And I'll just use this rough space over here to divide 2 by 11 again. So I get the sequence 0.1818 and so on. The number 1 and 8 repeat themselves. So again, here I have a non-terminating yet recurring decimal expansion. The last sixth part is the number 329 by 400. The decimal expansion for 329 by 400, I can maybe just write this as 3.29 divided by 4. It'll mean the same thing. And the division for this will become slightly easier for me. and it comes out to be 0.8225. This is a terminating decimal expansion. Now we move on to question 2 of the exercise. Question 2 says, you know that 1 by 7 is equal to 0.142857, repeating the 6 digits. Can you predict what the decimal expansions of 2 by 7, 3 by 7, 4 by 7, 5 by 7 and 6 by 7 are without actually doing the long division? And if so, how? And there's a hint over here that says study the remainders while finding the value of 1 by 7 carefully. So in order to know the decimal expansions for 2 by 7, 3 by 7, 4 by 7, 5 by 7 and 6 by 7, we don't really need to do the long division over again. We've already done it for 1 by 7, so we can just simply use that. And in order to know that, I'll do the long division for 1 by 7 and we're going to observe the remainders over here. I'm going to show you the long division of 1 by 7 and we'll get our answer from there. Here gives us a remainder of 3. This gives us a remainder of 2. This gives us a remainder of 6. Here we get a remainder of 4. Here we get a remainder of 5. And then again we get a remainder of 1, after which the sequence will repeat itself. So I'm just going to highlight the remainders over here that we have been getting. At first we had a remainder of 3, then we had a remainder of 2, followed by 6, followed by 4, followed by 5, followed by 1. So essentially we got all the remainders 1, 2, 3, 4, 5 and 6 in our long division. So hence, now if I were to do the long division of 2 by 7, I would essentially be doing the long division from this point, right? Which means this part of my sequence would repeat itself. So which would mean 2 by 7 would be 0.285714, and this sequence would repeat itself. Similarly, if I was doing 3 by 7, I would essentially be starting from this point right here, which would mean my decimal expansion would begin with the quotient 4. And hence this would be 0.428571, after which it would repeat itself. If I did 4 by 7, I would essentially be starting from this point here, which means my quotient would be starting from 5. So it'd be 5, 7, 1, 4, 2, 8, and this sequence would repeat itself. For 5 by 7, I'd be starting from this point. And hence my decimal expansion would begin from the quotient 7. So it would be 7, 1, 4, 2, 8, 5, and then it would repeat itself. For 6 by 7, we'd start here. And it would be 0.857142 repeating itself. So essentially, just by knowing the decimal expansion of 1 by 7 and observing the remainders while we see its long division, we can get the decimal expansions for 2 by 7, 3 by 7, 4 by 7, 5 by 7, and 6 by 7 without actually having to do the long division again. We'll move to the third question of the exercise. It says, express the following in the form P by Q, where P and Q are integers and Q is not equal to 0. It has 3 parts. So here we have 0.6 with a bar over the 6, which means 6 is repeating itself. Now, there's a simple technique to do this, right? We assume this number to be x, right? And now what we're going to see is how many digits after the decimal point is the repetition happening. So it's just a single 6 digit which is repeating itself, right? So we'll multiply 10x on both sides of the equations, and this is what we will get. And then what we can do is we'll label these equations, equation number 1 and equation number 2, and we'll just subtract equation number 2 from equation number 1. So on the left side we get 10x minus x, and over here we get 6.6 with a bar over the 6 minus 0.6 with a bar over the 6, which makes it 9x equals 6, or x is equal to 6 by 9, which in its simplified form is nothing but 2 by 3. And that's our representation in the form P by Q, where Q is not equal to 0. There's a way to cross-check our answer here as well. I'm just going to use this as a rough portion of my sheet, and 2 by 3, I'm going to do the long division. As we can see, the number 6 is repeating itself. So this validates, the long division validates our answer. The 2 by 3 is in fact correct. Moving on to the second part, it says 0.47 with the bar only on top of the 7. So here, in order to convert this in the decimal form, we'll use the same technique. We'll assume the number x to be 0.47 bar over the 7, which means over here 10x would be 4.7 with the bar over the 7, and 100x would be 47.7 with the bar over the 7. So we want to ensure that we subtract equations in such a way that we get rid of this decimal expansion. And in order to do that, we'll label these equations again. This is equation 1, equation 2, and equation 3. Here I'm going to subtract equation 3 and equation 2. So I get 100x minus 10x on the left hand side, and I get 47.7 with the bar minus 4.7 with the bar on the right hand side. This gives me 90x on the left hand side and 43 on the right hand side, and hence x is equal to 43 by 90. Now we can cross-check the solution as well by doing the long division. I'm not going to do it in this video, but you can do it yourself, and you'll notice that when you divide 90 from 43, you get this exact decimal expansion. Now the third part of this question is 0.001 with the bar over 0, 0 and 1. Here, same procedure. We'll assume this number to be x. However, over here, I'm gonna multiply 1000 with the number x. And why is that? I want to capture this entire decimal place. So if I multiply it by 1000, that's when it's gonna repeat itself from the point of decimal onwards. Since there are 3 digits, 0, 0 and 1 over here that are repeating itself. So when I multiply this by 1000, I get 1.001, where 0, 0 and 1 are repeating themselves again. And essentially I'm doing this because I want the decimal expansion after the decimal point to remain the same when I subtract in order to get rid of it. So again, if I label this equation 1 and this equation 2, I'm going to subtract equation 2 from equation 1, and we're going to get 1000x minus x on the left hand side, and this is what we're going to get on the right hand side. This is going to give us 999x is equal to 1, and x is equal to 1 by 999. So question number 4 is an interesting one. It's asking us to express the number 0.99999 repeating itself in the form p by q. And it's asking us if we're surprised by the answer and why does it make sense. Before we get to that, let's try and solve this and see why it's interesting. Now I can express this as 0.9 bar with the bar over the 9, indicating that the number 9 is repeating itself. Now in order to represent this in the form p by q, we'll use the same method. We'll assume this number to be x, and since only a single digit after the decimal point is repeating itself, I only need to shift the decimal place by 1 more, so I'll multiply this by 10x on both sides. This is what it will give me. This is my first equation. This is my second equation. I'll do equation 2 minus equation 1. This gives me 10x minus x on the left hand side. 9.9 with the bar on the 9 minus 0.9 with the bar on the 9. I get 9x on the left hand side. I get 9 on the right hand side. X is equal to 9 divided by 9, which is actually 1. Now, here's where it's interesting. The number 0.9999999 and so on isn't exactly 1, but when we're representing it in the form p by q, our answer comes out to be 1. That's interesting. We know they're not the same. So how is that even possible? And why does it even make sense? So the reason is that when we're representing the number in the form p by q, we're not exactly representing it the exact way it is. It's simply a closest representation of this, right? And why is this? Where in our entire process of converting it in the form p by q did we do anything suspicious that would make it seem like that? It's in the step right here. So the assumption that we've made in this statement is that if we subtract 0.9 with 9 repeating itself from the number 9.9 with 9 repeating itself, the entire decimal expansion over here cuts itself out and we're only left with 9. This is a gross assumption we've made. It isn't exactly true, since the sequence goes on for infinite number of times, and it's almost like subtracting an infinite digit from another infinite digit. The answer is never 0 in that case. However, the assumption over here is that it reduces itself completely. When we're converting a recurring decimal expansion in the form p by q, in most cases we are taking the closest approximation. We're not exactly doing this. And hence, in this case, when we took an approximation, we also inherently said that the closest number p by q, which is closest to this particular number out here, is the number 1. Moving on to question number 5. Question number 5 says, what can be the maximum number of digits in the repeating block of digits in the decimal expansion of 1 by 17? Perform the division to check your answer. So, one of the properties of repetition or the repeating decimal block is that if we're dividing 1 by 17, the maximum number of remainders that we can get are 16 before it starts repeating itself. And hence, the number of digits in the block that repeats itself will be 16 or below. Anything less than 17 is possible. We can check this by doing the long division ourselves over here. So here we go. I'm gonna continue this out here. So here on, this entire sequence will keep repeating itself. And let's count the number of digits. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. So anything less than 17 could be the final answer. Here we have 16. The next question, question number 6 says, look at several examples of rational numbers in the form p by q, where p and q are integers with no common factors other than 1 and having a terminating decimal representation in its expansion. Can you guess what property q must satisfy? Let's say 0.56. Let's take the example 0.1. Let's take the example 0.0012. Let's take the example 3.2. And let's take the example 1.5. Right. Now let's convert all of these in the form p by q. So the first one is clearly 56 by 100. In its simplest form, we divide numerator and denominator by the number 4 and we get 14 by 25. The next one, 1 by 10. The next one, 12 divided by 1, 2, 3, 4. 4 zeros out here, which is divide numerator as well as the denominator by 4 and we get 3 by 2500. Next we have 3.2 which is 32 by 10 or 16 by 5. 1.5 is 15 by 10, or this can be represented as 3 by 2. Just for clarity, I'm going to write all the numbers here, and then we're going to see if there is anything in the denominator which appeals to us. Can you guess it? Here, what is common in all of these denominators is that these denominators are a multiple of 2 or 5 or both. So which means in the first one, the denominator is 5 into 5. The second one is 5 into 2. Third one is 5 into 5 into 5 into 5 into 2 into 2. Next one's 5, next one's 2. So as long as the denominator is a multiple of 5 and 2's, or some combination of it when we're multiplying it, the entire fraction will always be terminating. And you can check it in other examples as well, not just the ones I have taken. Now we come to the next question, which is question number 7. It's asking us to write 3 numbers whose decimal expansions are non-terminating and non-recurring. So essentially, irrational numbers in the form of their decimal expansions. Sure, and it's pretty easy to do that. All we need to do is find a pattern which is non-terminating and non-recurring. So for example, 1.01001, 0001, 0001, and so on. Here, the number of zeros keep increasing after the 1, and hence we cannot find a block of digits which will repeat itself. So here's one example. Another example could be 2.1212211 2222111 2222111, and so on. Now here, the 2 and 1 repeats itself 1 time each, and then twice here again, thrice here, 4 times here, 4 times here, and so on. Again, we won't be able to find a block of digits which will repeat itself. So this is non-terminating and non-recurring. Another third example could be anyone. Let's say 7.171771771 4 times 7, 1, and so on. Right? Here again, there is a pattern to this. This decimal expansion can keep going on unlimited number of times, and yet we do not find a block of digits which is repeating itself. Hence, this is another number which is non-terminating and non-recurring. So we get 3 numbers out here, and we can have infinitely number of more. Moving on to the next question, question number 8. It's asking us to find 3 different irrational numbers between the numbers 5 by 7 and 9 by 11. Now, Irrational numbers, it'll be easier to find irrational numbers when we have these in decimal forms. So let's get the decimal forms of these. Just gonna use space on the right side as a rough sheet. So 5 by 7 is 0.714285, repeating itself. And similarly, I did the long division of 9 by 11, and it's 0.81, where the digits 8 and 1 repeat themselves. The question is asking us to find 3 different irrational numbers between these numbers, and it's really simple from here on. We know that one of the properties of irrational numbers is that they have a non-terminating and a non-recurring sequence. And it's easy to find that between these two numbers, right? So to give you one example, it could be 0.72772772 times 72 and so on. This number is bigger than this one, obviously less than this one. We can know that by just the first 2 decimal places over here. And this pattern is non-terminating as well as non-recurring. Similarly, a second one could be 0.7373373 times 3, 4 times 3, 5 times 3, and so on and so forth. Again, non-terminating, non-recurring, greater than the first number, less than the second number. Another third number could be 0.74, 744, 7444, 4 times 4, and so on. Again, non-terminating, non-recurring, greater than 5 by 7, less than 9 by 11, irrational number. This gives us 3 irrational numbers between these 2 numbers. And that's your solution. You can obviously have unlimited number of solutions for this. I've just written 3 of them. This brings us to the last question of this exercise. It has 5 parts. We're going to go through them one by one. The question says, classify the following numbers as rational or irrational. The first one is under root 23. The number 23 is not a perfect square, and hence root 23 will give us a non-terminating, non-recurring sequence. If you are interested to know what that is, it's somewhere between 4.7958, so on. The digits do not repeat themselves. It's hard to find a pattern unless you take the digits up to numerous number of cases. But however, know that under root 23 is an irrational number. Second part is under root 225. 225 is a perfect square. 225 is the square of the number 15. So under root 225 is 15. 15 is definitely a rational number, since it is in the form p by q, where q is not equal to 0. Third part, 0.3796. This is already in its decimal form. It is a terminating decimal sequence, and hence it is a rational number. Fourth part says 7.4 7, 8, 4, 7, 8, and so on. Here we see that the digits 4, 7, and 8 are repeating themselves. We can represent this in this form. So we know that although it is a non-terminating sequence, it is still a recurring sequence. And by that definition, this number is a rational number. The fifth one is 1.101.001.001 4 times 0, 1, and so on. Now we've done enough in this exercise to know that this is an irrational number. This, being a non-terminating sequence, is also a non-recurring sequence. We can't find a group or a block of digits that repeat itself, although there is a pattern that goes on indefinitely. And by that definition, this is an irrational number. And that completes this entire exercise. Thank you for watching this video. In case of any questions, any comments, you can leave a comment below, or you can reach out to me in my email ID at the description. Thank you for watching.